Constant motion problems. Now remember in K1 when we did simple kind of DTV and change in velocity type questions with acceleration as a review from grade 10? Well, these things are exactly like K1. They're pretty much identical, just a bit harder. That's it, okay? Same idea, same types of equations. I'm going to give you 2 more equations to work with, so you're going to have 4 equations in total, and it's just up to you to solve these problems. These physics equations, these 4 of them, show up for the rest of your physics life. You can't get rid of them, so you might as well learn how to do them now. Get really good at solving these things because they show up in every single unit. They show up all the time in grade 12. You just can't get rid of them. Okay. Yes, you do get them on a formula sheet at some point in the future, but like you will do enough practice that you just memorize them. Okay. So before we jump in, remember the change in symbol. When you put a little delta in front, it means your final minus your initial. You're changing something. So the 2 equations. We'll start with equation 1 and 2. Okay. This equation here, we'll do it in purple. Change in x is equal to average velocity times change in time. That's just a fancy way of saying this is your DTV. Okay, that's all it is. That's all that formula is. Your distance, your change in distance is going to be your average velocity times the change in time. This thing right here, right, that's just your average velocity. There's nothing new about that. Same thing with this second equation. This is the one that I like. This is super useful for finding changes in velocities, right? So you can use this to find either v initial or v final really easily once you have an acceleration, or find the acceleration if you're given a change in speed. So those are kind of our basic, we know how to use those already. 3 and 4 is where things get interesting. This number 3, I like to call this one the Holy Grail. Okay, that means you use it a lot. Use it a lot. Okay, it's super powerful. It's used in a bunch of different ways, and it goes like this. You've got a change in distance, a change in displacement is going to equal your initial velocity times a change in time plus 1/2 acceleration times your change in time squared. This one is super nice. I'm not gonna lie, I usually just write my change in times as time because we're looking at time intervals. So these old delta t's can just drop to t's, which is totally cool. But this formula is super nice when I would say use when your initial velocity is equal to 0. Okay, when that's something like starting at rest. When you start at rest, this formula is fantastic. Okay, if you don't, it's still really good, but when it starts at rest, it's even better because all you're dealing with is distance, acceleration, and time. Those are your 3 variables. Okay. Now there's the one last one that's also super powerful. It looks like this. It's your final velocity squared, which is equal to your initial velocity squared plus 2a delta x. This delta x just a change in distance, right? So if you're changing velocity, then you're also changing a distance, which means you have to have some change in distance. This formula is super fantastic when there's no time given, right? If you don't have a time, that's totally fine. You can still do questions even if you don't have time. So if you're not given a time, maybe you need to solve for it, but equation number 4 is really, really nice when there's no time. Okay, so you put all these things together, you need to get really comfortable and know exactly how to use each one of these equations and when you should use each one. Okay, so example number 1, we've got Hobbs walking at a speed of 1.5, sees a bunny, bolts after it for 7 seconds, and then he reaches a speed of 10 meters per second. What is his acceleration? So one strategy I like when you solve these problems, write out everything you have. You've got an initial velocity of 1.5 meters per second. You've got a time of 7 seconds, and you've got a final velocity of 10 meters per second, and we want the acceleration. Okay, now if we look at our formulas, use number 2. It's fantastic. This is just like the warm-up that we did before, so that's all good. V final is equal to V initial plus AT. We're going to get 10. Sorry, we're going to get our V final minus our V initial is equal to our acceleration times time. So our acceleration is just V final minus V initial divided by our time. We've done this before. Punch in your numbers. 10 minus 1.5. Divide that by 7, and you should get a nice number of 1.2 meters per second squared is your acceleration. So that's fantastic. Okay. Part B says now he gets tired. He's gonna slow down. It gives you a rate here, slowing down of 0.8 meters per second. You can try this one on your own. I'll just give you a hint. The answer, we're looking for the time. It's 10.6 seconds. So go ahead, try that one on your own and see if you can get the answer. All right. Let's look at question number 2. Okay, a little bit more fun. We've got a ball rolling down a hill starting from rest. Starting from rest is super important to recognize that means that your initial velocity is going to be 0. It's accelerating down the hill. Makes sense because the thing's rolling down a hill. We want to know what's the velocity of the ball after 4 seconds. We just did a question exactly like this, right? Final velocity is equal to our initial velocity plus your acceleration times time. We're looking for the final velocity, so this second equation is really, really nice. Our final velocity is, our initial velocity, sorry, is just going to be 0. That goes away. And our final velocity is just going to be whatever our acceleration is times how long we're accelerating for, which means our final velocity is 12 meters per second. There's nothing fancy about that. But part B, we want to know how far it travels. Before I introduced these 2 new equations, we didn't have a way to find distance when you have an object that's accelerating. But now, equation number 3 is really, really nice because we can find distance when it comes to accelerating objects. So use number 3 to find the distance, okay? The distance traveled, okay? And it's also really nice because our initial velocity is 0, it simplifies very nice, simplifies nice, okay? So our third equation, x is VIT plus 1/2 AT squared. There's the holy grail right there. And right away, since we start at rest, we can get rid of this term, that 0, since it starts at rest. That's fantastic, which means all we're looking at now is the distance is just going to be 1/2 AT squared. Super nice. We don't even need part A for this. We're given the acceleration. We're given the time. We can just punch in our numbers. 1/2. Our acceleration is 3. That's fantastic. Our time is 4 seconds. You punch that in, you do the math, and you should get 24 meters. Okay? Great example of using that third equation. Question number 3 and 4 we're going to do in class together. So I want you to try this one on your own. Okay, same thing with this one. We'll do them in class. This number 4 is exactly the same at number 2. Okay, same formula, you just have to do some algebra. So look back at the question we just did right up here. Question number 5, we'll do this one together. This is a reaction time question. A little bit more involved, a little bit more to it. So let's see what happens. We've got a driver traveling at 90 kilometers an hour. When a deer runs out 50 meters ahead of them, it takes you 0.45 seconds to react, and then you slam on the brakes, and then you slow down with a constant acceleration of 8.5 meters per second squared. We want to know, do you hit the deer? So it's always fun with these questions to draw a picture. There's my little car. I'm going this way. It's great. All of a sudden, nice little deer over here. Blah, blah, blah. We want to know, does this thing, do we hit the deer? Okay, and we know that we have 50 meters here to work with. Okay, so there's going to be 2 parts to this question. The first part is how far does it take to actually react to the deer, right? During this time, we are not stopping. We are literally just traveling for 0.45 seconds. We are just, it's like nothing has even happened. So we can figure out, all right, well, our distance of the reaction is just going to be our time times the velocity we're going at, which means we're just going to be, we'll do that calculation after. The second part of this is once we start actually slowing down, I'll call this dA, we're still going to travel. Yes, we're slowing down, but now we have an acceleration of negative 8.5 meters per second squared. That negative is very important because we are slowing down. Okay, so there's two parts to this question. There's the original reaction time distance that you go, and then the secondary acceleration distance that you go. So we need to find both those distances and see if that's less than 50 meters. So that's the goal. We're going to look at dr plus dA and see if it's indeed less than 50 meters. That's the goal. Okay, so this first one, reaction time, pretty straightforward. Our velocity, that's our initial velocity, 90 meters per second, or sorry, 90 kilometers per hour, which is going to equal, if we do a quick little calculation here, we're going to get 25 meters per second, okay? Which means the reaction time distance that we're going to go 0.45 times 25 meters per second. So we are going to travel a distance of 11.3 meters before we even start slowing down. Okay, that's no problem. Now let's figure out, all right, well, now that we started slowing down, we want to figure out a distance. We've got an acceleration. We don't have a time, right? Which means if we don't have a time, let's look at this equation. Plus 2AD, okay? This equation, well, we know our final velocity. Our final velocity is going to be 0 since we are stopping. We know our initial velocity because we knew how fast we were going, and we know what our acceleration is. So let's just go ahead and solve this. We're going to get negative vi squared, right? Because we're going to cancel out this final velocity, and then we're going to move this initial velocity over. And then we are going to, so that's going to be equal to 2AD. We're looking for a distance, we'll call it the time during acceleration. Negative vi squared divided by 2a. Let's just go ahead, plug these numbers in. Negative 25 squared all over 2 times negative 8.5. Those negatives are super important because they cancel each other out. We can go ahead, plug that into our calculators, and you should get a number of 36.7 meters. So we travel that while stopping. So in total, if we want to know if we hit the deer, well, our reaction time distance plus our acceleration distance is going to be 11.3 meters plus 36.7 meters, which means you add those together, you're going to get 48 meters. And since that's less than 50 meters, because it told us that the deer was 50 meters ahead of us, therefore the deer is saved, and we are happy. Okay, that's one of the most involved questions that we'll do. 2 parts, we've got a reaction time and an acceleration time.